Good morning, Professor. Good morning, classmates. In this opportunity, I'm going to present a WSGG correlation based on high temp 2010 for computation of thermal radiation in non-isotherm and non-homogeneous water and carbon dioxide mixtures. As summary, we have introduction. In this work, we are going to have introduction, methodology, result and discussion, conclusion, and reference. As introduction, we can talk about radiation. Radiation in participating gases is crucial in combustion processes, but its modeling is complex due is too much complex due to strong variations in temperature, composition, and the highly irregular behavior of spectral properties. The development of high-resolution database, particularly HiTem 2010, has made it possible to significantly improve the accuracy of variety models at high temperatures. Although advanced models such as SLW, CW, and K distribution use detailed spectral information directly, their high computational cost limits their use in coupled simulations. But the WSGG model, despite its simplicity, remains attractive due to its robustness and efficiency, provided that reliable coefficients are reliable. This work presents new WSGG coefficients fitted from line-by-line data generated with HiTem 2010 for typical air-fired combustion products, water and carbon dioxide mixtures. The coefficients cover wide range of temperature and pressures, and validation is non-isothermal and non-homogeneous media show good agreement with the LBA results, confirming that WSGG remains an efficient and accurate option for fast radiative heat transfer calculation in combustion process. Okay, we are going to talk about spectral model. First, we have a generation of spectral lines. In this opportunity, the radiation in participating gases originate from vibration-rotation transitions, whose spectral lines are described by Lorentz profiles. Based on the HiTem 2010 database, the spectral absorption coefficients of water and carbon dioxide are generated incorporating collisional bonding, temperature and pressure dependence, and the integrated intensity each line by line. Figure 1a, this figure here in the left side of the slide, shows an example of a spectral absorption coefficient of water vapor, highlighting the strong irregularity of the spectrum. For mixtures, the total absorption coefficient is obtained as the weighted sum of the individual contribution of each species. As we can see here, we have a lot of lines of spectral for water mixtures, right? So in this work, we are going to have to paste from these figures 1a to a figure B, but we are going to use, for this case, a WSGG model. Good. So now, talking about model weighted sum of gray gases, WSGG, the WSGG, this is where we are talking about now, this model, approximates the real spectrum by reduced number of gray gases with constant absorption. As we have seen before, this figure here. In this illustrated figure 1b, the total emittance of the medium is expressed as a weighted sum of ray contribution, whose weights depend on the temperature and are fitted from data obtained through line-by-line integration. Although the model implies a strong spectral simplification, as you can see here, we are taking a constant sites And fitting coefficients can be used to solve general radiative transfer problems while maintaining energy conservation. Good, very well. Now we are going to have how to determine the this kind of coefficients, right? By line integration. So in this opportunity, we are going to talk about total emittance defined through line by line integration. So the WSGG model coefficients are obtained by fitting 528 total emittance values computed through line-by-line integration for water and carbon dioxide mixtures with pressure radius of 1/1 and 2/1 over all temperature range from 400 to 2500 Kelvin and pressure path lengths of 0.0001 to 10 atmosphere per meters using the Levenberg-McQuarrie method. The resulting coefficients are presented in the following tables, in the table 2 and the table 3. We can see here the coefficients that they were made determined by Levenberg-McQuarrie method. So the model validation is shown in figures 2 and figures 3, as we can see here. In figure 2 and figure 3, we can look at them where the emittance calculated with a WSGG model, here for example, are compared with those obtained using line-by-line integration for different pressure path lengths. As we can see here, we have many different pressure path lengths values. And we can see here, right, for three models we are talking about, the three ones are very accurate. And the emittance calculated with WSGG model are compared with those obtained using the L by line method for different pressure path length values here, right? So an excellent agreement is observed over the entire temperature range here, right? Or over the whole range of temperature, where we can see an excellent agreement with average errors below 1 to 1.1%, even for long path, as we can see here, long path of 10 atmosphere per meters in both radius, 1/1 and 1/2, right? Finally, a figure 4, as we can see here in the right side, this figure evaluates the hypothesis of independence of absorbed coefficient with respect to the partial pressure, showing that the errors remains moderate and acceptable for typical air-fired combustion conditions. We can see here where we have a very high in this kind of temperatures, but at low temperatures we have total emittance high, right? We have high total emittance here, as we can see. And at high temperatures, we have a very low total emittance for very different pressures, partial pressures, as we can see here, right? For different radius too, for radius of 1 and 2, we can see here, right? So saying this, now we are going to talk about the WSGG model and radiative transfer equations. Okay, continue with the radiative transfer equation. We can say the radiative transfer in non-scattering participating media is described by the spectral radiative transfer equation, as we can see here, right? We can see the first equation of these slides is called the radiative transfer equation. So we in this case, in all the cases, we have, our objective is resolve this equation. And to resolve this equation, we're going to use the WSGG model, right? So let's continue. Radiative transfer equation, non-scattering participating media, is described by this equation, which accounts for local absorption and emission by the medium. We can see here, right? And where I eta is intensity and I eta B is intensity of a black surface, right? So to obtain the total radiative flux, the RTE must be integrated over all the entire spectrum and on all the directions. So this equation should be integrated in all the directions and all the spectrum entire. So what can we do? When the WSGG model is applied, the entire spectrum is decomposed into finite number of gray gases, as we can see as summatory here, so that the total radiative intensity is a given direction is obtained as the sum of partial intensities, as we can see here, partial intensities, no, as we can see, associate with each gray gas. This is what the WSGG model is talking about. Well, for each of them, a radiative transfer equation analogous to the spectral one is solved by using a constant absorption coefficient. So we are going to assume that this coefficient pressure is constant in a few difference of number wave number, and a temperature dependent weighting factor too. So although the absorption coefficient of each gray gas is constant, the model can be applied to non-isothermal and non-homogeneous media, since temperature and species concentrations are evaluated locally, right? Because we are going to evaluate the species concentration and temperatures by local. So saying this, we can say that the spatial solution of the RTE is carried out using the discrete ordinates method applied to one-dimensional slab geometry, in which the participating medium is confined between two parallel walls, as schematically shown in this figure, in figure 5. We can see here an schematic, a one-dimensional domain of this article. So we can see we have a S, which is the distance between the walls, and we have a S, which is the center point or any point of the line here, right? On the line that is staying in the middle of these walls. So as we can see the equations of 17A and 17B, we can take look that it has a plus signal and minus signal. So that's because we have a plus signal in the direction of that intensity and a minus signal in the contrary direction of that intensity. So after solving these equations, the net radiative heat flux and volumetric source in positions S respectively can be determined by this equation, which we are going to see now, 18A and 18B. All right? Então, let's going to take place now a result and discussion, and we are going to talk about now of that topic. Okay? So, okay, the evaluation of the WSGG model is carried out by considering a non-isothermal and a non-homogeneous medium confined between two parallel blocks walls as illustrated before in figure 5. Three temperature profiles, as we can see here, equation 19, 20, and 21, and three carbon dioxide molar concentration profiles, as we can see here, equation 22, 23, and 24, are going to be analyzed. All defined along the dimensional coordinates S in all the cases. The various temperature is fixed at 1100 Kelvin and the various concentration of carbon dioxide at 0.1, ensuring a common basis for comparison. Figures 6a and 6b show the temperature and concentration profiles employed. All right? Okay. So we can see here in the figure 6a that we have a different temperature profiles, right? So we can see that we have a profile very slow, as we can see a black line continuously. We can see that this line is a parabolic form, and we have another line that is a little bit more pronunciated, that we have a change of temperature very high here. And that's only the profile temperatures that we are going to study in this section, right? And the same thing to concentration, right? So the L by L, line by line solutions are generated from a spectra computed for temperatures between 400 and 1800 Kelvin, and partial pressure of carbon dioxide and water between 0.01 and 1 atmosphere with linear interpolation applied for intermediate values. Both the WSGG and L by L simulation are solved using 200 spatial elements and 30 discrete directions, ensuring grid independent solution. All right. The accuracy of the WSGG model is evaluated through local maximum and various errors in the radiative heat flux and volumetric radiative source as defined in equations 25a and 25b. This is we are going to see in a table 4 that we are going to explain later. Okay. So in this case, we're going to talk about a simple symmetric profiles. All right, we're going to use here equations, this equation 19, 20, 21 to do these figures. Okay, we're going to make an analysis of these figures now. For symmetric temperature and concentration profiles with maximum at the center of the domain. So we can see here, right, in the figure 7a and 7b show, no, we can be, that figure shows the radiative heat flux in the A form, in the figure A, and the volumetric source in the figure B, right? For a relation of concentration, the water and carbon dioxide of 2, and path lengths of, as we can see here, path lengths of 0.5, right? 1 and 2 meters. The relative heat flux is 0, as we can see here, 0 in the center of the domain due to symmetry. We can see that it has a symmetric form, right? Whereas the volumetric source that we have here in the right side in the figure 7b reach its maximum absolute values in this region, right? So we have a maximum in a zero value of source heat flux, right? We can see in these figures, right? Okay, what does it indicate? It indicates that net loss of energy by radiation. So we are going to losing radiation by energy, right? So increasing the distance between the walls and hence relative heat transfer due to the increase in optical thickness. We can see if we get increase this distance S, if we're going to increase, we are going to have enhanced walls and relative heat transfer due to the increase in optical thickness. In all cases, the agreement between the WSGG and L by L models is very satisfactory, right? So we can see that the WSGG model in L by L method, we can see here that it has the same form in both ones, right? So that's a good form. That's a good satisfactory. As quantified in table 4, okay, we are going to explain later, where the maximum and average errors remain below 4.18% and 3.28% respectively. For the same case, but with the ratio of concentration of water and carbon dioxide equal to 1, figures 8a and 8b show similar behaviors. We can see we have the similar behaviors in both ratios of concentration. Concentration of water over carbon dioxide of 2 that we are seeing before here, and in concentration of water and carbon dioxide of 2 that we're going to see here, we have the same behavior of the components in this WSGG and L by L methods, right? So with smaller magnitudes, we have the same computation with smaller magnitudes due to the reduction in participation spaces, right? We have in this kind, we can see the behaviors with the smaller magnitudes due to the reduction, right? The reduction in participating spaces. The corresponding errors also include in table 4 exhibit magnitudes comparable of those of the case with higher relative concentrations, higher relative concentration of water vapors, right? We can see here. Both has the same behavior. That indicates that our model WSGG is making a very well work, right? So let's continue with analysis. Now we have the symmetric profiles with higher gradients of temperatures, right? We have the figures 9a and 9v. So here we don't have a very slow gradient of temperature and concentration. We now have a little bit higher gradients of temperature and concentration, as we can look at figures 9a and 9b. In these figures A and B correspond to temperature and concentration profiles that are still symmetric but with double gradients. So we're going to we increase the gradients of temperature and concentration. Since the variation occur over half the distance, the relative heat flux vanishes not only at the center of the domain. So we have to remember that the past figure we have here just a point, but now we just here a very constant line practically, right? We have here a line constant in a very distance, right? In an interval of distance, approximately 0.3 to 0.7, right? We don't have here a point. We have here a constant distance, right? So The radiative heat flux, as we can see in figure 9a, vanishes not only at the center, right, at the center of the domain, but also at the location of maximum temperatures. Here too, we can see we have here and we have here too, right? What that's a very complicated behavior. That exhibiting this kind of behavior is a very complex behavior too, right? Despite this, the WSGG model reproduced the L by L solution satisfactorily. So, as we have just a line in the center or just a point in the center, we can look beside of this, we can look at the WSGG model defined very well, is very well accurate to the L by L method, right? It's a good, it's a good modeling. So in this case, the maximum in the various errors limited to the 3.14% and 1.43% for the radiative flux and 7.63% and 2.57% for the volumetric source there as reported in table 4. So here we have a relative source, right? We remember that in the last figures, in the past figures, we just have just one just one falling of source height relative flux here, right? But now we have just 1, 2, 3, 4, right? Two up and two down. So, but in this case, what is important is that get realize that the WSGG method is modeling, right? Modeling a very well comparison with L by L method, right? Both methods, L by L and WSGG, describe the same behavior of the height uh, equation radiative, right? Or the height radiative transfer, right? That's a very well. So let's continue. In this kind of figure, in figure 10, we have an asymmetric. Remember that the two figures before we are going to have with symmetric, but now we have asymmetric profiles, as we can see in figure 10a and 10b. The third case, in this case, not case, the third case, we are going to consider asymmetric profiles. What is that? How can we get this? We get this with a very strong change in temperature and concentration. The different wall temperatures are 880 and 400 Kelvin. In these figures as we can see here, figure 10a shows that the location where the relative heat flux is zero is shift. We can see here where this is the location of the relative heat flux is shift, right? Reflecting the thermal and compositional asymmetry, right? Remember that the two figures past, we don't have this kind. We have now this kind because of the asymmetric form of this relative heat flux, right? In regions, in the same figure, in regions low concentration, as we can see here, at low concentrations, right? We have low concentrations. We can see too that a low concentration, both radiative heat flux and radiative heat source go to zero, right? We can see here when we have low concentrations, both radiative heat flux and radiative heat source goes to zero, right? As we can see the figure, we can realize that. In figure 10V, this figure 10V, we can indicate that the volumetric source reaches its maximum at the location of maximum temperature and concentration. We can see here the maximum of this figure we can see that it has the maximum value when it reaches its maximum at the location of maximum temperature. We can see here maximum temperature and concentration. The agreement between WSGG and L by L remains very good. So again, we can see that L by L and WSGG method for all the distance S are or describe the same behavior of the test. So we remember that we talked about before about some symmetric when we have not changed very strong the temperature and concentration, but now we are going to make a variation very stronger of temperature and concentration. And at high variation, a stronger variation of temperature and concentration, we can see that our model, WSGG model, is very accurate to L by L method. So at this point, the model that we are seeing, WSGG, is describing very well the behavior of these scenes, right? So now we are going to discuss the global error discussion, table 4, a maximum and a very errors of the WSGG solution for the radiative heat flux and radiative heat source, right? We have here a ratio of concentration of water and carbon dioxide of 1 and 2. We have here a distance, and we have here a volumetric source heat, and here a radiative heat flux, right? So the result summarizing, this is a summarize, right? The result in summarizing table 4, together with figures 7 to 10, show that the accuracy of the WSGG model is not significantly affected by temperature gradients. As we have seen before, we have worked with profiles where the temperature is not stronger, has not a stronger variation. In the figure 10, we are going to work with a very strong variation of temperature. In both cases, we have a very significantly accurate our method, that is WSGG, with the L by L integrating method. So additional cases with constant concentration of the carbon dioxide present errors of similar magnitudes, which highlights the difficulty of correlation the model errors with a single physical parameter. Finally, the global average, we can see here, average of radiative heat source and average, right, of a average of a heat transfer, radiative heat flux transfer, right? So we can see here that we have an error of the order of 5% maximum and 2% average, right? We can see here 5% maximum here, 5% maximum, and 2% mean, right? That is very well, which constitute a reasonable estimate of the expected performance of the WSGG model in this non-isothermal and non-homogeneous media. To finalize, to sum up, we can conclude that this work presents new WSGG correlation for mixture of water and carbon dioxide obtained from feeding total emittance data calculated by line method. Using the heightened 2010 spectral database, the correlations are valid for partial pressure radius of 1 and 2, path lengths between 0.001 and 10 atmosphere per meters, and temperatures in the range of 400 and 2500 Kelvin. The purpose correlations allow the total emittance of the medium to be calculated with high accuracy, which is useful for global engineering estimates, such as those based on the mean radiative path lengths. More importantly, these correlations can be used directly in the spectral integration of the radiative transfer equation, RTE, enabling the solution of general thermal radiation problems in non-isothermal and non-homogeneous media. The validity of the model was evaluated through the several test cases with different temperature, with a stronger temperature, with a very slow temperature and concentration changes, And we can see that the WSGG results with L by L reference solution are very accurate. The results showed a remarkable consistency of the model with combinator errors in an order of 5% maximum and a 2% average, even under severe conditions with large thermal and compositional variations. Although the WSGG model is not intended to replace detailed spectral methods as a reference tool, its robustness, energetic consistency, and high computational efficiency make it viable and reliable alternative for engineers application in which thermal radiation is part of a concept of a complex, very complex system with multiple coupled phenomena. This is all. Thank you very much. I guess this presentation likes you. Thank you very much.